Very good.
Morning, everyone. How y'all feeling? All right, so my main objective for today is making sure everyone feels as prepared and comfortable heading into the exam as possible. This is our last day of class, but I'll still be in the building today and on Thursday to help anyone with any study questions at the time. And also, I encourage you to email me, again, literally any time you have a question pop up. Floor will be open to any questions or concerns you guys have, potentially related to, say, the exam itself, study guide, homeworks and quizzes that you're working on, makeup lab even, anything at all. Reminder that there are 5 exam time slots to choose from, and that the practice test is definitely longer and more difficult than the exam itself. So if you're looking at that and if you are concerned at all, I'm trying to say that as a comfort. So, what's on your minds? Wait, for part B?
Part A, y20 wouldn't be negative.
So the object is slowing down, but its final speed is still pointing in the same direction. So it's initially going 45 forwards, and then it slows down to 20 forwards. Those are the same direction, so when you plug them in, they would have the same sign as they are being plugged in. But then the equation inherently would have a negative in it, so final minus initial, positive 20 minus positive 45. So the final velocity still points forward, but your acceleration is negative because you were slowing down. And as a result, the 20 remains positive when I say use it to figure out the distance traveled within the final minute.
And for the seconds in that equation, why wouldn't it be 60 seconds minus 2 seconds?
So it says we're driving at 45 meters per second for 1 minute. So that's the first period of time here. Then you hit the brake and decelerate to 20 meters per second over a period of 2 seconds. So the second period of time I showed here is the 2-second deceleration. You only move 65 meters forward during that time. Then after that, you then drive at 20 meters per second for another minute after my intent was after you slowed down, before the car gets out of the way. So after reaching 20, you move at 20 for 60 seconds. That's my intent when writing it.
You can go to any exam slot, right?
Yes, you can come to any one of those 5 times. And you only have to come to one. It's not like a multi-part exam or anything. Also bring your formula sheet. I want to make that clear. If it wasn't already, bring your formula sheet. You could use your formula sheet. And you could write all over it. Yes?
Is it gonna be on paper again?
The test?
Yeah.
Yes. The formatting will be pretty much the same as the 2 previous tests. It's just longer. Anything else on your minds for right now? All right. Well, while I've got the practice exam up, I want to kind of just thumb through it briefly to try to point out some things that I definitively want you to know and make sure you know to be able to do on the exam itself based on what I have on the practice version. So first, you need to be able to calculate the weight of an object. And if I ask you, how do you calculate the weight of an object, what should your answer be? Yes, either m times lowercase g, or there is secretly another answer, the big gravity formula, big G times m1 times m2 over r squared. Again, weight and force of gravity are not the same as mass. I'm only pointing it out because someone always writes it a way that makes me sad, so I just want to make sure everyone knows. If you ever need weight or force of gravity within a question, it's always going to be m times negative 9.8 because you can always assume something takes place on Earth unless I tell you otherwise. You also are going to have to be able to identify Newton's laws, just like on test number 1. So if you want to check how it was written on test 1, again, if you don't have your copy of the first test, if you never collected it from me, you can grab it from me, I still have them. On test 1, the question had 5 statements that you had to pick the laws of motion out of, both identifying them and also numbering them accordingly. So, of the 5 statements, 3 are laws of motion, 2 of them are not laws of motion. The 2 extra statements might be true and might be false, they just aren't laws of motion. So you have to identify them and put the right number to them. You don't have to say write them from memory, but you have to identify them. On the practice test, I asked you to just write them, because again, the practice test is meant to be the more difficult of the two. But to quickly review them in order, first law is called the law of inertia because an object's inertia is its innate property to keep doing what it is already doing. Its inertia tells it, stay at rest if you're at rest, stay at constant speed if you're moving at constant speed, until acted upon by an outside imbalanced force. So, first law is the law of inertia, rest at rest, motion in motion until acted upon. Second law is F equals ma. We often abbreviate it to just the formula here in the class, but if I was to say, use words to describe it instead, as you might see on the test, this law says that if an imbalanced net force acts on a mass, that mass will begin accelerating proportional to the mass and the force. So, imbalanced forces cause acceleration. And the third law is the action-reaction law. If A acts on B, B acts back on A in the opposite direction. So again, identify them out of the lineup even if they are not worded exactly the same way. You have to be able to analyze them for meaning. You do have to know the difference between centripetal and centrifugal. To quickly review, centrifugal is the fake one that feels like it's pointing out of the circle. Centripetal is the real one that pulls towards the center of circular orbit. Fugal, F stands for fake. Capital P stands for pretty real. 7 and 8 are both examples of vector addition, being able to use the Pythagorean theorem, the trig information that we've been utilizing throughout the semester. 9 is projectile motion. Say if something is in free fall through the air, like you launched it off of a building, for example, if it's a projectile, it is falling, therefore its acceleration is negative 9.8 in the y and 0 in the x. You need to be able to use that information to assume the object's trajectory, figure out how long it's going to be in the air based on its y acceleration, and know that its constant x motion is going to carry it a certain distance within that amount of time. Number 10 talks about friction, specifically how friction works on slopes. So if you don't already have this triangle on your formula sheet, this triangle referencing the relationship between gravity, normal force, and friction on a slope, and how the three of them form a right triangle together, you should put this on your formula sheet. Basically, these three forces, and this current angle is as if the slope looks like this. Gravity still points down because the Earth didn't go anywhere. Normal force now points at a slope because it has to be perpendicular to the surface that created it. And friction has to be parallel to the surface creating it because it's the surface trying to stop you from sliding along itself. So the friction has to be parallel to the ramp, normal force perpendicular, and gravity still points straight down because the core of the Earth doesn't care if you're standing on a hill. These three forces can be dragged and arranged into this triangle to represent the trigonometric relationship between all of them. Gravity still points straight down. Normal force is perpendicular to the force of friction because, again, they are respectively perpendicular and parallel to the ramp's surface. And since they're perpendicular to each other, the right angle of the triangle goes there. Meanwhile, the angle of the slope goes here between normal force and gravity. So if you have a ramp like this, these three forces will interact with each other like this. So not only do you have to be able to do this specific trig, remember again how friction works. The surface itself is trying to stop motion along its surface. There's two types of friction, and friction equals normal force times the corresponding mu. So 10 references the triangle and how friction is acting in this scenario. Bless you. 11 also involves friction. In this one, you would have to say pick out the difference between kinetic friction and static friction. However, my previous section asked me a question about this one, and I realized that at some point there was some sort of a flaw in the way that I wrote it, because you could do it two different ways to get two different answers, as opposed to two different ways getting the same answer, which is what I prefer. And for that reason, I'm going to recommend that this not be the best question to study. There's clearly a flaw in it somewhere that I didn't catch when I was writing it, and there are, in retrospect, there are better examples of how you need to be able to use this information on this practice exam. So for number 11, I would really just glance at it to remind yourself of the difference between static and kinetic friction. Basically, if you set up this assembly and it starts moving, what type of friction is going to act on the sliding box? Yeah, kinetic. If the object is in motion, it's kinetic, and if the object is not moving, it's static. That's the main thing I want you to just glance at this and know. Again, for the math, I wouldn't spend any time doing the math for this one, because again, I've realized it's not a good practice question for this particular exam. There are other questions on the practice exam that better represent what you need to do with this information. So you can skip 11 with the caveat that you do still need to be able to tell the difference between kinetic and static friction. I would instead draw your attention to 14 as an example of the energy transformation aspect that I try to do in my work for number 11. For this one again, 14 represents a situation where energy is going to change between states. It goes from EPE while the spring is coiled, kinetic energy while the object is launching, and then GPE when the object is at its maximum height. And in the work here I show the relationships between those different stages, show the conservation of energy throughout the entire process. So 14 is a better representation of that part, and 10 is a better representation of what I want you to be able to do for friction. So 11, just look at it, remind yourself the difference between static and kinetic. Don't waste your time on the math, there's better examples elsewhere. 12 is a collision question. I show work here for treating it both inelastically and elastically. You do need to know the difference. You should be able to do it both types. Difference again is momentum is conserved across both, which is why in my work for both I show conservation of momentum. But in the elastic version, the objects tend to bounce away from each other at different final speeds, and kinetic energy is also conserved. So even though you have two unknowns, you can use a second equation with the same two unknowns in it. So glance through that, make sure you can work the two different ways. 13 is an orbit question. We have a satellite orbiting Earth. I mean, things you should remember about that are in space, gravity is acting as a centripetal force. Some real thing always has to play the part of centripetal force, and that means that whatever your centripetal force formula is, it can always be set equal to whatever force is playing that role. And again, in space, gravity tends to do that. So literally, the start of an orbit question is setting the two things equal to each other and plugging in their respective formulas. This formula for finding the force of gravity between the satellite and the planet, this formula for showing how that gravity is going to act as a centripetal force on the satellite. And from there, you need to be able to identify what things cancel across both sides and what you are actually solving for. In this question, I asked for orbital radius, which is again the distance from core to core. Orbital radius because the core of the satellite orbits the core of the Earth, and the core of each object is the center of their gravitational effect. So both R's across both sides, regardless of what centripetal force formula you use, it's the same R, it's all orbital radius, and that is what I asked you to solve for. No, I didn't ask you to solve for orbital radius. I asked you to solve for launch velocity, excuse me. But the R is orbital radius. That's a term you should remember. The R here is orbital radius, and it's the same across both sides. Additionally, one of the masses will be repeated across both sides, and in this case, that is the mass of the satellite. Note that the mass that remained throughout the rest of my work is the mass of the planet, because it's the satellite's mass that appears on both sides and cancels out. The mass of the planet does not. The satellite's mass is here because it is the orbiting object moving at this velocity. And since the satellite's mass cancels out, that should tell you that any object, regardless of its mass, would need to move at the same speed to orbit at the same distance, orbit at the same height above the ground, even if it was the size of the moon. So, remember again, force of gravity equals centripetal force. Note what things are the same across both sides and proceed from there. 14 is, again, a good example of energy conversions. 15 is rotation, various aspects of rotation and how it relates back to the linear counterpart of each thing. 16 is also both linear energy and rotational energy, how the two of them work together. 17 is power. It is good to be able to convert things into and out of horsepowers, for example. 18 and also I think 21 later on are both torque questions. 19 and 20 rather. My formatting got messed up here. 19 and 20 are both waves. 19 is wave speed, 20 is Doppler effect. 21 is torque. 22 is pressure and buoyancy. It's technically slightly easier to float in syrup because it's denser than seawater, but I still wouldn't recommend it. And lastly, 23, what type of wave is sound? Longitudinal mechanical, yeah. Mechanical meaning it requires a medium, it needs air or water or dirt to travel through, and that's why you can't hear in space. Longitudinal meaning that it is a pressure wave that vibrates in the same axis as travel, not like light, which does shake like an ocean wave. So, sound wave is longitudinal mechanical. How do you guys feel? So, again, with the exception of 11, if you can do the practice exam, I think you'll be more than capable for the exam itself. Said exam is 16 questions. This is 22 if you ignore 11. Again, this is meant to be more difficult because I'd rather you make the mistakes here. I know I've said that 8 million times, but I teach this lecture 3 times in a row and I don't always remember who I told what. Anything else on your minds for right now? All right. Well, this is the last normal day of class. I will be in the building both today and on Thursday if you have any questions, and I also still encourage you to email me literally anytime. Before we break though, I have one more thing to show you. An unfortunate downside of this particular course, Physics 1500, is that it doesn't involve thermal energy. Thermal energy comes up in 1510, meaning we don't get to set anything on fire in 1500. Let's fix that. So, you may have noticed that the standing wave generator that I've been using for the past week is no longer hooked up. Instead, it's been replaced with this big cylinder. This will still allow me to generate standing waves, except instead of making them on a string, I'm going to make them in gas and therefore also in fire. You probably smelled when I turned the gas on. This tube is currently connected to standard gas hookup. So the cylinder is filling with flammable gas, and there is a bunch of holes poked in the top of it. So as the cylinder fills up with gas, eventually the gas is going to come out the bottom, which I've now set on fire. So every hole now has flame emerging from it. Since there's constantly new gas coming into the tube, that said, that's going to push more gas out the top, and it will just be on fire as it does so. And it is totally safe as long as your eyebrows are not directly next to it. And this is pretty enough to look at. You could roast marshmallows over it. But that's not all we're going to do with it, because this tube has speakers installed in both ends. The same speakers as the standing wave generator. You can probably see the wire and the device itself on either end. And those speakers are still connected to the frequency generators that we've been using all week. And so I am going to blast sound into the gas of this tube, and we're going to see what happens. First I'm going to cut the lights so the gas, so the fire is easier to see. Yeah, that's good. And I'll cut the projector as well. Where did my thing go? Everyone can see? All right, so now I'm going to cut on the speakers. These speakers are going to make a much more pronounced noise, just a disclaimer. The frequencies will be higher, meaning that you can hear them, and the whole system kind of acts as an amplifier. So things might get loud at certain points. You've been warned, but please feel free to cover your ears at any given time if things get uncomfortable. When I kick these things on, it's first going to start at 100 hertz. Note that immediately caused a change in the fire. Cut them off real quick just to show. Wait a minute. Cutting these on causes the columns of fire to jump up a little bit because, again, sound is a longitudinal mechanical wave. So this speaker creates a pressure wave that vibrates areas of high and low pressure all the way over to the other side. And since it's a mechanical wave, in addition to longitudinal, it requires air, or in this case, get flammable gas to travel through. And that means that the physical vibrations cause the gas to separate itself into pockets of high pressure and low pressure. I said again, sound is a pressure wave. So areas of high pressure will cause the gas to physically be forced out of the tubes more strongly than normal. Now, right now we're at 100 hertz. This is one of the lower frequencies humans can hear. I'm going to crank this up to about 264 hertz. And if I increase the amplitude just a little bit, you can see it actually takes the shape of the same standing waves we were making all last week. This happens to be the second harmonic frequency of this particular tube. I calculated most of them on Friday night. And this is just the frequency that creates a second harmonic standing wave through gas on this particular size object. So note that that's higher than the frequencies of last week because the string is a different object to the gas, different properties, different wave speeds. And to show again, they're both currently set to this, and we've created a second harmonic standing wave on fire as opposed to string. And I can increase that frequency to create different harmonics. So 396 should be third harmonic. So 3 tongues of fire instead of 2. See if I can get fourth to work. Alright, I'm going to increase the amplitude a little bit, see if we can see the 4 columns of fire. There we go. And this is happening invisibly with every sound you ever make. Sometimes if you just play music into like a cloud of dust, you might get an effect like this, but I think it's just cooler with flames. This object, this whole assembly, is called a Ruben's tube, same as a Reuben sandwich. And people build these to create the same effect, and some people build them to play music through. So there's probably at least one video on YouTube of someone doing Carol of the Bells through one of these things. This cannot play music, unfortunately. I didn't build it. One of our very talented previous professors did. But unfortunately, there's no aux port or anything. It only plays pure tones. But if you've done anything with music before, you probably know that if you play different frequencies at the same time, you'll get a beat, which can cause the fire to fluctuate. Ooh, that's a new one. There we go. That's what I was looking for. I gotta write that one down. So that is a beat. The frequencies don't quite match up, and as a result, they don't add up normally. They're kind of like moving past each other constantly and only adding up periodically. So the wave isn't properly standing. It is traveling at a different speed, and you can get moving fire. So, this is one of my favorite demonstrations to do on occasion. Oh, it's an amplitude difference that does it. Okay. Questions? Again, this is called a Ruben's tube. I might actually be able to find a clip or two. Cut the amplitude to be less annoying. Oh wow, you can see the gas interrupting the projection. Oh, it's not spelled the same as the sandwich, I'm mistaken. I don't have the ability to project audio, but there's loads of videos on YouTube of people making these with actual music. Some people even make Ruben's boards which is a full two-dimensional plane full of holes, and you can see the fire really dancing in multiple axes that way. So, something to look up if you're bored.
That guy looks scary though.
I mean,
It's
it
like
can
in his
be.
back, like in his garage. He just kind of looks like an arsonist.
Okay, the difference between science and messing around is one, being careful, and two, writing your results down. That's all it takes to do science. So as long as he's recording his data and not dying, then he's technically a scientist. Questions? All right. Anything on your mind? I say question. Anything on your mind at all, serious or silly, before we close lecture for the semester? Yes.
Are you sure it's not about to explode?
This, it shouldn't be about to explode, but for safety purposes, I can cut off the gas. The sound waves shouldn't cause anything to explode. Although, actually, since I have a minute to talk about silly things, you know how opera singers can sing glass to make it shatter? Sound can make things break. The way that works is using a principle called resonant frequency. Nah, not a sound effect. There's a slow-mo video that I just remembered existed. Here we go. There we go. So, this is an example of how sound can make something blow up. That speaker is going to produce various frequencies until it tunes itself to the resonant frequency of the glass. Every object has what's called a resonant frequency, and that is the frequency it most likes to shake at. If you emit sound waves at something at that correct frequency, the object likes vibrating at that frequency. If you ever messed with a tuning fork before, you'd know, say if you have two forks of the same frequency and you get one of them going, the other's just going to spontaneously start shaking because the sound waves from one will travel and strike the other, and as long as they're the right sound waves, it's going to want to resonate at that frequency. And if you keep adding more sound waves, the object is just going to keep shaking more and more and more, driving up the amplitude of its own oscillation. Just realized this isn't the video I was remembering. Driving up the amplitude of its own oscillation. Just the one. Yeah. Literally causing the object to vibrate and flex in ways it's not meant to. This is literally what the glass is doing if you slow the video down. And if you keep adding more vibrations, it's going to keep shaking more and more and more and more until it flexes beyond what it can recover from and it breaks. Every object has a resonant frequency, meaning every object can shatter if you play the right sound at it. That includes wine glasses, that includes rocks, that includes humans. It also includes bridges, because one bridge fell over because the wind naturally drove it at its own resonant frequency. If you've ever heard of galloping Gertie, old name for an old bridge. This is what happens when construction workers don't take physics class and don't know what resonant frequency is. Hello? Good to look ahead. There we go. So again, any object, once driven at its resonant frequency, is just going to keep shaking more and more and more until it vibrates itself apart, or the vibrations, like the source, stops. The wind caused this because the wind drove it at its resonant frequency until it literally shook itself apart. This was the Tacoma Narrows Bridge, emphasis on was, referred to colloquially as galloping Gertie. just for a sense of scale, it's an old car, but it's still a, come on. That is a whole car being lifted, you know, several feet into the air. It also had a dog in it, which someone did successfully walk over and collect before this happened. If you keep driving something at its resonant frequency, it will shatter. Thankfully, the resonant frequency of this thing is not playable on these speakers. So, technically sound can blow things up, but this shouldn't explode as long as I'm managing the gas levels correctly.
But
Any other
humans
questions?
can?
Sorry?
Humans can explode?
Humans can.
Is that spontaneous human combustion?
Well, it shouldn't be combustion. It would look more like just popping. So I guess content ID warning real quick. Technically, again, the human body is not one solid object, so it would kind of be hard to play one frequency to cause the entire human to do that. But there have been enough movies and video games where people have scream powers that people have done the math to try to find the resonant frequency of just a human skull. And if that frequency was blasted into your head long enough, your skull would shatter. That said, your brain would probably be reduced to mush prior to that happening. But there's YouTube videos about the math for that, because again, enough people in media have sonic screams that people have asked that question. Anything else on your minds? All right. I know if you have any other questions, needs, or thoughts, serious or silly. And if we don't see you again before the exam, it's been a pleasure. I think you're all going to be great. And have a good day.
Thank you.
Welcome. Nice to have you. Occasionally. Yeah, me too.